So we're back, and so if you recall, we were discussing this subject, which is how is it that you get non-thermal particles. Non-thermal particles meaning this is the number of particles as a function of energy, and this is clearly not a Maxwellian. This is a power law, right? And these are what are called non-thermal particles. This is what we were discussing. So what we said was that these non-thermal particles are produced as a result of collisions in a phenomenological acceleration region. Okay, and the requirement is that in each collision there is an energy gain, and this beta is larger than 1. Maybe I should write it here. Beta is larger than 1. So this would be the energy gain after k collisions. However, it's not as if the particle, the given particle which is getting accelerated, can just get accelerated indefinitely. It's not like that. What's in fact happening is that after each collision there is a certain probability p, which is less than 1, that the particle can actually escape the acceleration region. Okay, so the particle can escape the acceleration region with a probability p less than 1, and so after k collisions what happens is the energy of the particle is beta raised to k, and after k collisions the number of particles remaining in the acceleration region is given by this, and taken together it results in this kind of a power law distribution of particles, which is clearly non-thermal and which is what we are talking about, right? Now, one important thing to remember is that you require that E is equal to beta E naught, beta greater than 1 in each collision. In other words, you require an energy gain in each collision. Okay, so whatever the collisions with these scattering centers are, you want to ensure that there's an energy gain in each collision, so that with each successive collision the energy of the particle keeps increasing. Now let's think a little bit about what kind of situation would ensure that there's an energy gain in each collision. Okay, so now let us think of a particle and a scattering center. So this would be the particle which is destined to gain energy, and this would be a scattering center. In fact, in the original formulation by Fermi, I believe it was in 1950 if I'm not mistaken, but in the original formulation by Fermi simply, Enrico Fermi, the famous Italian astrophysicist, he thought of the particles as some phenomenological particles and the scattering centers as large immobile clouds. Okay, so which is why I've drawn it this way. Here's a particle and here's a scattering center, and the particle is essentially a test particle. What do I mean by that? It's a test particle in the sense that whatever happens to this particle hardly affects the scattering center. The scattering center is some sort of a large cloud. It's a huge rock, for instance, and it's hardly affected by what happens. Think of the particle as a light table tennis or a ping pong ball, and think of the scattering center as a large table tennis racket. Okay, so you know, when you hit a little table tennis ball with a table tennis racket, there's hardly any recoil on the racket, whereas the light ball, it goes bouncing off, right? So this is what happens, right? So that's exactly the kind of situation we are envisaging. So this would be a large scattering center. Okay, but even so, I think this is 1950. I would urge you to check this treatment of scattering. Okay, so now consider an approaching collision. Consider a situation where either the particle or the scattering center or both are approaching each other like this. Okay. So, consider a situation where the particle and the scattering center are approaching each other. So, consider an approaching collision. Right? And in such a situation, in such an approaching collision kind of situation, where this guy is moving this way and the scattering center is also moving this way. Okay. Or you can transform frames such that maybe one is stationary and the other one. Either way, you understand what an approaching collision is. An approaching collision would be one where there is the particle definitely gains energy. Okay. And I would also say an approaching inelastic collision. Inelastic, right? The collision is inelastic, that's why there is an energy gain. So, in an approaching collision, the particle definitely gains energy. This fellow, this particle definitely gains energy. Whereas, in an overtaking collision, one where the particle is here and the scattering center is here, and the particle is moving in this direction and the scattering center is also moving in this direction, and the particle is trying to overtake the scattering center, right? The particle loses energy. Right? So, in this case, the E equals, if you write down the energy of the particle as this, E equals beta raised to k, or in a single collision, E is equal to beta times E naught. The beta would be larger than 1 in an approaching collision, right? And in an overtaking collision, the beta would be less than 1. Okay, so this is clear, and clearly in our treatment here, we have assumed we want beta to be larger than 1. In other words, we want approaching collisions. Okay, so we essentially, since we need in E equals beta times E naught for each collision, okay, for beta larger than 1, we need approaching collisions. Okay, so this is the situation that we're talking about. We would like a situation where the scattering center is always approaching the particle, okay, and the particle always gains energy with each collision. And of course, it's not as if the particle will keep encountering more and more scattering centers as time goes by. Otherwise, the particle would just simply, amass infinite amounts of energy, and that would, that would create problems. So we say that, yeah, the particle gains energy with each successive collision, approaching collisions to be precise. And, as time goes on, the particle has a finite probability of leaving this scattering center, leaving this region filled with scattering centers, and therefore the number of accelerated particles goes down. Okay, so this is the kind of situation we're talking about. Now, what does this have to do with shocks, you might ask? Because, that's the whole point. We are, after all, talking about shocks as agents of particle acceleration. So, what does this have to do with shocks? So, let us now consider a shock like this. Yeah, so this would be the shock. And now we're not talking about particles anymore, we are talking about the fluid, the low energy, the background fluid, which forms a shock. Okay, so this is the shock, and this is the frame of the lab frame. This is as observed in the lab frame. As observed lab frame, the shock is moving ahead with a velocity u. okay, and there's a downstream region characterized by some some density rho 1, some temperature T1 and some pressure P1, and there's an upstream region. So this would be the downstream region and this would be the upstream region, and this is characterized by some density rho 2, T2 and P2, right? And we know that the whole point of a shock is that there's a very definite relationship, there's a very definite jump right here at the shock. For the time being, we just idealize the shock as an infinitely thin discontinuity, okay, and there's a very definite relationship between rho 1 and rho 2, T1 and T2, P1 and P2. We know this. And so let's consider a shock, yeah, which is moving like so. And you've got scattering centers embedded in both these. So you've got scattering centers here and you've got scattering centers here as well. The scattering centers are not part of the fluid, are not part of the background either, of the background fluid. Neither the scattering centers nor the energetic particles are part of the background fluid, okay, but the scattering centers are carried along by the fluid. Okay, the scattering centers are frozen into the fluid. If the fluid is moving, the scattering centers also move with the fluid. Okay, so you've got scattering centers both in the downstream region as well as the upstream region, and they are simply moving along with the fluid. The scattering centers are not part of the background fluid. Maybe think of the background fluid as something blue, the scattering centers as something black, and maybe the particles which are destined to get accelerated as red. Okay, and the scattering centers are also few and far between, and so are the accelerated particles which are destined to get accelerated. They are also few and far between. Whereas a background fluid, there are so many background low energy particles that you just observe them as a blue continuum. Okay, so here you have a shock moving like so, and this is how this picture looks like in the lab frame. Now let us consider how it would look like in the shock frame. In other words, you climb onto the shock in the frame of the shock. In other words, here is an observer who is sitting on the shock, right? So as far as this observer is concerned, the shock is stationary. Yeah, so in the shock frame, the shock is stationary, obviously. Yeah, so you've got a shock which is stationary, yeah, and because the shock is stationary, it does not have a velocity u, but for the observer sitting on the shock, he or she will find that the fluid in here is rushing towards the shock with a velocity u. So therefore, the V1 here is equal to like that, moving this way. Okay, and we know that there's a very definite relationship between the velocity here and the velocity here. Yeah, and let us consider an infinitely strong shock for which the Rankine-Hugoniot conditions are satisfied, right? The Rankine-Hugoniot conditions for an infinitely strong shock are satisfied. So we know that there's a factor of 4 difference between the velocity here and the velocity here, right? So here what happens is you have the fluid is moving. This is all in the shock frame. The fluid is moving with a velocity v2 which is equal to 1/4 of v1, right? And this is assuming an infinitely strong shock. But the point is, you have v1 which is u and v2 which is 1/4 of u1. This is in the shock frame. Okay, where are we going with all this? You will see in a minute. Okay, all right, so let us now go into the frame of the downstream frame. Okay, in the downstream frame, however, In other words, let us go back here in this frame. So we now want to climb into the frame where the fluid on the downstream side is at rest. Okay, so how do I do that? I go from the shock frame, I subtract a velocity v1, okay, and that brings me into the frame where this stuff is at rest, right? So I subtract the velocity v1, and so you've got the shock here, and here the velocity is 0 because I'm at rest, but here you see I've got fluid rushing, okay, towards me with 3/4 u. Why is that? You can see that from here. So you see you've got v1 coming to the left, right? And so what I want to make this 0, right? So I add a velocity u, rightward velocity u here, that makes it 0, and if I add a rightward velocity here equal to u, okay, so I have u minus 1/4 of v1, which is u, and that gives me a 3/4 u coming towards the right. Now what do I have here? I've got lots of scattering centers. I've got scattering centers which I'm going to denote by these squiggly lines. Okay, so consider accelerated particles which are advected along with the, so these would be particles which are destined to get accelerated. Okay, they are being swept from the left to the right, and the reason, and here is the reason for calling this diffusive shock acceleration. What happens is in the vicinity of the shock there are enough scattering centers so that these particles can diffuse over from this side to this side. Once they diffuse over to this side, okay, so or for that matter they can diffuse over from this side to this side. Okay, so once they diffuse over to this side, okay, the particles are sitting here, okay, and they have equilibrated with the fluid here, okay, so they are at rest, but you see there are scattering centers embedded with the fluid on both sides. Okay, so they are at rest essentially, and what they observe is that there are scattering centers from the left approaching them with a velocity 3/4 u. So they are approaching the particles that are destined to be accelerated. So you've got approaching collisions. You've got particles that used to be here which diffusively crossed over to this side, and once they've crossed over to this side they equilibrate and they become part of the downstream fluid, okay, and they're just sitting there happily just waiting around. What they see is that they are approached by scattering centers which are approaching them at a speed 3/4 u, and they experience approaching collisions, and we know what happens during approaching collisions. The beta is larger than 1 and the particles gain energy. Okay, so this is very important. So they gain energy when they are embedded in the downstream fluid. So they gain energy as a result of these approaching collisions. Okay, fine. So they gain energy. They got one hit from these paddles which are approaching them. So fine. Okay. Now what happens is, let us now draw this shock again, except now we want to draw this in the upstream frame. Okay, this was in the downstream frame. Okay, now I want to remain in the upstream frame. In other words, I want to make this velocity 0. I want to make this velocity 0 so that I can be at rest in this frame. That's what upstream frame means, right? How do I do that? Well, I add a leftward directed velocity equal to 3/4 u. If I do that, this becomes 0, but of course this out here I have to do the same on both sides, right? So out here I get a 3/4 u moving to the left, right? And that's what happens here. So here I've got rest frame. That's what I mean by these squiggly lines. The fluid is not moving, but on the other hand, here I've got fluid moving at 3/4 u. Okay? Maybe I should have a mod sign here too. So here I've got fluid. As far as the upstream frame goes, if I was in the upstream frame, I would see the fluid rushing towards me with a velocity 3/4 u. Okay, now what happened to these accelerated particles here? It gained energy. Yeah, it gains energy, so that's fine. But after it gained energy due to the approaching collisions from scattering centers on the from the upstream side, it was on the downstream side, and scattering centers from the upstream side approach them, yeah, and they hit them, bam, and they gain energy. Now after that, what happens is they diffusively cross over to the to this side, and that's the whole point. Diffusion is a very important. The ability to diffuse on both sides of the shock is a very important aspect of this problem. If you do not have diffusion, this whole process will not work. Okay, so they diffusively cross over to this side, and now they are like this. Yeah, they've diffusively crossed over to the upstream side, and they equilibrate with the upstream frame. In other words, in the upstream frame, they are at rest. So the particles are here. They are happily sitting in the upstream frame. They have already gained energy due to one collision, and they are happily at rest. Now what do they observe? Well, as we said, there are scattering centers on both sides, right? So even on this side, there are scattering centers, and these guys which have already gained energy due to one collision, right? They observe scattering centers again moving towards them at a velocity 3/4 u. And remember, this was also 3/4 u, and this is also 3/4 u. Okay, they observe, since they have equilibrated here, they now observe scattering centers moving towards them at a velocity 3/4 u. And again, you've got approaching collisions. Approaching collision again. Okay, they diffuse to the upstream side, and they again experience, an approaching collision. So they gain energy again. So what's really happening here is that particles repeatedly diffuse back and forth across the shock, right? In other words, from the upstream side to the downstream side and vice versa, they keep diffusing back and forth, okay? And in each, and after each shock crossing, after each crossing, they experience an approaching collision. That's the whole point, right? They experience an approaching collision after each shock crossing, i.e., repeated energy gains, right? So they repeatedly experience energy gains. So they diffuse back and forth across the shock, and after each crossing, they experience an approaching collision. From who? From the scattering centers that are embedded along with the flow. Okay, so therefore, you experience this kind of a situation with a beta greater than 1, because on each side of the shock, you have an approaching collision, so a beta is greater than 1. And since they are repeatedly doing this, after k collisions, so after k collisions, i.e., after k diffusive shock crossings, the energy of a given particle is beta raised to k e raised to 0, as we wanted. So here's a physical situation where this condition is satisfied. And of course, since the whole thing is diffusive, it's not as if particles can, sometimes, they diffuse back and forth, but they really do not have to remain in the vicinity of the shock always. They can diffuse a little farther away. Once they diffuse a little farther away, they'll find it difficult to come all the way close to the shock. And therefore, there is also escape, I should say. The diffusive nature also ensures escape with a probability p less than 1. In other words, after k crossings, the number of particles is equal to n naught p raised to k, where p is less than 1. And remember, these were the two ingredients that we needed. We needed this and we needed this, right? And you eliminate k between this, and you get a power law distribution in the number of n of e. These two result in an n of e, which goes as e raised to minus alpha. In other words, a non-thermal particle distribution. Okay. So this is an explicit demonstration of the phenomenon of diffusive, and diffusive is very important, shock acceleration. Diffusive shock acceleration of who? Of the test particles. Okay. By who? By the particles are accelerated by who? Well, they are accelerated via encounters, head-on encounters with scattering centers, which are embedded along with the fluid which flows with the shock. Okay. So the scattering centers are embedded in the fluid, and therefore they just simply obey whatever the fluid tells them to. If the fluid is flowing and if the flow has a certain discontinuity, well, they also flow with the same velocity. Okay. So it's important to clearly understand these frame transformations. This would be the lab frame, and this would be the shock frame, and this would be the downstream frame, and this would be the upstream frame. Really, in order to understand the fact that there are approaching collisions, all you need really is a downstream frame and the upstream frame. But in order to get to the downstream frame, the upstream frame, you need to go via the shock frame. So I urge you to turn this over in your head a little bit to understand how exactly the shock acceleration happens. And this treatment is taken from Longuer's book, High Energy Astrophysics. I believe this is by Cambridge University Press. So I urge you to look up this book, further details, and so this particular treatment is taken from there. And so what we have now done is we have shown, not shown, we have justified to some extent. We have the role of fluid shocks as particle accelerators. And I thought it was important to demonstrate this, even though particle acceleration as such is not really part of a fluid dynamics course, but in astrophysical fluid dynamics, shocks are simply agents for accelerating particles. So I thought it was important to sort of give you at least a brief flavor of how particle acceleration takes place before going on and examining how how shocks arise in astrophysical contexts and so on and so forth. So when we meet next, we will consider the formation of shocks in supernovae. Supernovae shocks are a very well studied phenomenon in astrophysics, and the predictions of the theory match the observations very well indeed. So when we meet next, we will consider spherically symmetric shocks in supernovae. And I also wanted to re-emphasize that shocks are to be found in all kinds of other astrophysical situations, such as near Earth shocks, the Earth's bow shock, shocks in accretion flows, shocks in supernovae, and so on and so forth. We will simply consider one of these situations, that of spherically symmetric shocks in supernovae. So that's it for now, and thank you.